a look at S-CP.A.2, worksheet number 1. It's all about independence. And independence is kind of the big idea that they wanted us to cover in geometry when it comes to probability. Now, independence implies that there's a compound event. So what it means to be a compound event is that two things happen. So independence doesn't matter if you're just picking one card from a deck. Independence doesn't matter if you're just rolling a dice. Independence doesn't matter if you're picking a marble from a bag. Independence matters when you are doing 2 marbles or 2 cards or 3 spins on a spinner. That's when you have to decide, are they independent of each other? So independence means to be unaffected by the other event that takes place. So whenever we talk about independence, we're talking about a compound event. Now, first of all, let's just figure out how do we calculate a compound event, and then we'll look at whether they're independent or not. So for instance, if you wanted to know what's the probability of flipping a coin, or actually let's do it getting a head on a coin and an ace in the deck. So you have your coin and you flip it. It's a 50-50 chance. So that would be 1/2 is the probability of getting a head. So over here, the probability of a head is 1/2. And the probability of getting an ace, there are 4 of them in the 52 cards that are there. So one thing I want you to notice is when we do an AND statement, when we're doing multiple events, it's becoming less likely, right? If I just say what's the chances of getting a head, that's just a 50-50 chance. And then I say and, so now it's kind of like narrowing it down. I need a head and I need to get an ace. And so things are getting like less likely. They're multiplying, generally they're becoming less likely. The probability is multiplying together. And so it's now 4 out of 104. So I guess the first thing I need you to understand is when you're doing an AND statement, the intersection of those that have heads and those that are aces it's just simply the multiplication of those two things. Now I want you to notice that the probabilities here are basically, the original probabilities are the same probabilities that calculate that intersection. And ultimately, I think you get that heads, flipping a head and picking an ace have nothing to do with each other. So in other words, if I knew that a head had been flipped, it wouldn't impact my choice of an ace at all, and the probabilities stay the same. This would be a good example of independent relationships. Now, but there aren't, all of the world is not always independent, and just some real world examples. Are height and weight independent? In other words, by knowing one, would it affect your understanding of the other? I think the answer is yes. If I told you the person is 20 pounds, I think you're not going to say, oh, that person is 6 feet, right? It's going to be a small person. And so you would actually, it would impact your knowledge. They would not be independent of each other. If I told you it's Wednesday and let's see what else, things that knowing the day of the week would not impact your height, for instance. So height and day of the week don't have any connection. They'd be independent of each other. So if I told you it was Monday, it wouldn't impact what you think someone's height is, or whether it's Friday, it wouldn't impact that. They're disconnected. They're independent of each other. Now there is a case to establish when things are independent. And you just saw it a minute ago, but it's a very important idea. This is a very, very big idea. and I'll do my best to kind of help you to understand it. This is the test for independence, or I guess the other way to say it is, if you're told things are independent, this is a true statement. And this statement basically is saying, if you have two original probabilities, whatever they are, the chances of getting a, well, let's use this little bag here as an example, okay? Let's see, we've got 1, 2, 3, 4, 5 white, 5 white out of the 8, and 3 out of 8 are. So white is the probability of A, and black is the probability of B. Now, if I want to know the probability of getting a white and a white, okay, so that would be the probability of white. So I went in there, grabbed a white. Now, here's where it becomes important. So I have my probability of white. If I replace it back into the bag, that probability is unchanged, right? It doesn't, you know what, let's leave it probability of white and black, let's say, just for the sake of the way it's set up. So by putting the marble back in, the second choice is not impacted by the first choice. That's independence. Keep an eye on that idea. So this would be 15/64. Now, because I put it back in, it maintained an independence. And so, again, the intersection will be created by just multiplying those two numbers together. Now, if something changed, for instance, if that marble had been kept out, then that second probability would have been impacted by that choice, and that is where we get dependence and we get into conditional relationships and so on, which is coming, don't worry. So the idea, though, is that if you go to the intersection, whatever it is, and it is simply the probability of A times B, then they were not impacted at all and they're independent. Do you get it? That if they don't get changed, if this guy does get changed, oh, there's one less white and there's one less marble or whatever, if this number starts changing, then it became a dependent environment. So the key is for independence, all things independent, if you can take the original probability of A and if you multiply it by the original probability of B, and it gives you that intersection, if it gives you that intersection, then they are independent. Let me just show you an example here to test if they are or are not independent. So let's say here is the probability of A and the probability of B. And we take our guy here, and the probability of A is 0.4. Notice 0.4. And the probability of B is 0.5. Now, when I multiply 0.4 times 0.5, I get 0.2. That number does not match the actual intersection. So this is an example of not independent relationships. Whatever A and B are, they impact each other. Had this number produced this value right here, then we would have said that they are, in fact, independent. Let me see if I can find a situation. Here's one. Let's see if this produces an independence. 0.25 here, 0.25 here, 0.25 here. So the probability of A is 0.5. The probability of B is 0.5, and they do equal 2.5. Whatever A and B are in this environment, they are independent because the probability of A times the probability of B gave me the probability of A and B. If they don't, something got changed and they are no longer independent of each other.